Thank you, Pete, for that introduction. Thanks to the NIH for providing this venue today. And most of all, thank you for your time and attention here. I want to start out with having you all imagine the following scene, very vividly. If it helps you to close your eyes, that's fine. Just imagine the following scene. You were at the doctor's office. It's time for your flu shot. The doctor lays his instruments of torture out in front of you. Okay, there's the alcohol wipe, there's the syringe, and there's the Band-Aid. Okay? He tells you what arm do you want it in. You say the left. Okay, roll up your sleeve. He takes a hold of your arm. His hand is cold, because they're always cold. He starts to wipe down a spot on your arm. He pops the cap off the syringe. He says, "This is going to hurt." Okay? You all imagining that? So what are you feeling in that moment? We've all been there before. Just reimagining it, we all have a sense of what's going to happen. It's probably going to be painful, right? Pain is imminent. We know that because we've been in the same situation before. There are certain cues that tell us that it's going to be painful. And I use this example because it gets into one aspect of cognition and really the human experience that I find absolutely fascinating, which is predicting the future, which we do all the time. On the one hand, this can be really, really good. This can be wonderful. It can be great because we can think that something is going to be good. We can think that based on something we do or based on certain contextual cues we see around us, something good is going to happen. And that's great. It gives us hope. It gives us some desire to do something. On the other hand, it can be absolutely petrifying. And this is also something I find interesting and also kind of funny. Because thinking about something really bad that might happen, whether it's pain, whether it's something really aversive, can be totally paralyzing, right? Do I tell my girlfriend the truth? She's going to be pissed. That's not good. I don't want that. So it's her fault for getting angry, so I'm not going to tell the truth. Yeah. Okay. But it's funny because sometimes what we predict is going to happen and what actually happens, there's a huge discrepancy sometimes. This is hilarious. This is really funny sometimes because we think, how could I think that an awful thing was going to happen and it actually did not? This discrepancy between what we predict and what actually happened is something called prediction error. And everything I've talked about so far, predicting, prediction error, and pain all take place in a region of the brain called the medial prefrontal cortex. It died. The big reveal. Just give me 1 second, guys.
We didn't predict that.
We did not predict this. You know, you never know what's going to happen. Put it back in. There we go. Okay. The medial prefrontal cortex is traditionally defined as everything in the medial wall anterior to the anterior commissure right here. Everything I've shaded in magenta is typically what people refer to when they talk about the medial prefrontal cortex. Now, I want to start out with some of the history of this region because it's been widely studied. It's one of the most widely studied regions in the brain. And around the year 2000, Bush and his colleagues came out with a paper describing a model about how they thought this part of the brain was organized. It happens to be involved in things like error detection, prediction, inhibition, working memory, a lot of different things, as well as pain. What they found was in this green region right here that I've shaded, we'll call this the dorsal anterior cingulate cortex for this talk. Okay, so roughly everything anterior to the anterior commissure, but right before you get to the genu of the corpus callosum. And they said that based on averaging across a bunch of different studies, this region can be most clearly defined as being responsible for more higher level cognitive processes. So things like your prediction error, your working memory, your inhibition, all of that is in the dorsal anterior cingulate cortex. On the other hand, everything that's more affective, the more, they say, hot parts of cognition sometimes. Things like IAPS photos. Has anybody dealt with IAPS photos? Seen them? Okay. Some of these things are absolutely disgusting and horrifying. Okay. They listed something called negative affect. Things that make you feel disgusted, anxious, depressed maybe, seem to be represented right here. Okay, so this was a model that had a lot of currency for a long period of time. And that distinction is something I want to come back to. The third part of the medial prefrontal cortex I'm going to be talking about today is something dorsal to the DACC called the pre-supplementary motor area, shaded in blue. Okay. So many years went by, and many studies were conducted, thousands, tens of thousands. And now we have the ability to do meta-analyses because we have a bunch of different studies studying a bunch of different things, and we can start to carry out meta-analyses in the medial prefrontal cortex. These figures are from a Nature Neuroscience paper by Alexander Shackman back in 2011. And he said that if you look at all these different studies where each of these red dots represents the peak activation for a single study, and you average them together, you look at the likelihood estimate for each of those classes of stimuli, you do a conjunction on them, and you happen to find that all of them are very overlapping in that part of the brain, suggesting that the dorsal anterior cingulate cortex, like I highlighted earlier, actually is involved in all of these classes of stimuli. It's not the case that there's this really clear distinction between the two. Now, are they interdigitated? Is it some kind of gradient? That wasn't really understood at the time. But this seemed to be the best estimate of what was going on. And it's reasonable from one point of view because the dorsal anterior cingulate is what they call ideally situated for a lot of things. One, you're more likely to get a significant result if you study this part of the brain. So that's one reason. Another reason is because it has a lot of reciprocal and dense connections between other parts of the brain. So for example, it has nociceptive inputs from the spinal thalamic nuclei. It has projections to the dorsolateral prefrontal cortex areas, thought to be involved in actually implementing cognitive control. It has projections to the more dorsal pre-SMA and the SMA just before that for things like motor planning, motor execution. So like I said, this is reasonable. This made a lot of sense. And now we get to where I start to come into the picture. Because very recently, about a year ago, there was another study that came out. And this one used another meta-analysis tool called NeuroSynth. I'm curious, if you haven't used it, it's a pretty interesting tool. If you ever want to do a meta-analysis, you can basically do it on the fly, and it's all online. So you enter a search term like pain, like prediction error, and you can do a lot of the same meta-analyses that people have been doing for many years. It gives you both reverse inference maps, if you want to know the probability of a search term given activation at a voxel, also forward inference. If I give you a search term, what's the probability of a certain voxel being active? This tool was used about a year ago in a paper that came out in the Proceedings of National Academy of Sciences, with their reputation for publishing non-inflammatory, non-controversial titles. This one really rocked a lot of the medial prefrontal cortex world because this made a very strong claim that the dorsal anterior cingulate cortex, contrary to this more integrationist model, this adaptive control hypothesis by Alexander Shackman, it's actually distinct. And this region is selective for processing pain. In their paper, they highlighted these two things. So everything behind this white line right here, and in blue is the dorsal anterior cingulate cortex. Everything above that in green is the pre-SMA/SMA. So first, what they looked at was, are people actually defining these boundaries appropriately? If you look at a meta-analysis and you look at things like a search term for dorsal anterior cingulate cortex or anterior cingulate cortex, the peaks and really the centers of masses of both of those seem to be more within the pre-SMA, suggesting that a lot of people, when they're reporting results, actually are not within the dorsal anterior cingulate cortex, but rather in a region just dorsal to that. So that's step one, if you accept the boundaries that they listed out on this diagram right here. We'll get back to that in a second. So looking across these constructs like pain, if you look at pain, for example, and can you guys see the white outlines at the very bottom? That's the dorsal anterior cingulate cortex. The one up here is the pre-SMA. And if you look at a reverse inference map, you see that the majority of activation is within the dorsal anterior cingulate cortex. There's also a lot of stuff outside of it, but don't pay any attention to that. We're not going to focus on that. You've been trained to just focus on your region. But if you look at things like conflict, you look at working memory, there's more cognitive aspects. you find that they seem to fall, at least based on these meta-analyses, more within the pre-supplementary motor area, suggesting that there is a distinction between the two. So pain is more ventral down here. Everything else seems to get shoved up into the pre-SMA. Interesting. So everybody was totally cool with that, right? No. No, people freaked out, and there were a lot of different papers that got published trying to rebut it. And how to rebut that, but with your own meta-analysis. Okay? We live in a time where there are blogs, and any random person can say whatever the heck they want. And this is good sometimes because you can have a lot of back and forth, a lot of debates about what might be the best practice for really trying to tease apart how this region of the brain is organized. Again, it's a very popular region to study. And there have been other meta-analyses and other machine learning tools that have been trying to say that actually it's not selected for pain. If you look at these other meta-analyses we're doing, if you do the posterior probabilities right, you actually find that it's not just selected for pain, but actually a broad range of other things. So, what we started to think was, well, everybody in these meta-analysis studies is saying, wouldn't it be great if somebody actually did a study that had both pain and some of these cognitive constructs within subjects, and then we might be able to say something a little bit more accurate about it. But nobody did. So I remember when I was a young man in graduate school, and we were talking with a couple of postdocs about this. We're talking about this in the break room. We're hashing out how we're going to actually approach this, how we're going to tease apart this in our own study. We're talking about the details, and at some point I go, yeah, we should do that. We should do that. The postdocs look at me, they look back at each other, and they go, what do you mean we're going to do it? Okay, you're going to take care of that. So over the next year or so, I ran a lot of subjects for it, and we want to tap into these two main questions. Is the dorsal anterior cingulate really selected for pain? And second, are cognitive effects really represented within the pre-SMA? The two main questions here. Now, before I get into the experimental design, I want to point out a few issues with some of these meta-analyses. The reason that they're talking about why a within-subject study would be so good is for a few reasons. One, meta-analyses tend to focus only on the peaks of activations and ignore the spread of activation across everything else. Number two, you fail to account for individual anatomical variability, a very important point I'm going to get back to later. And number three, you can also have some studies that are overrepresented. Either they've been done more, or they may have better experimental control, or maybe the search terms you're using are more specific to that construct that you want to look at. So the way we addressed this was based on a paradigm by Esther Arts. This is a diagram. I'm adapting this from her study back in 2011, which was using predictive cues in a spatial Stroop context. So if I give you a cue, let's say a green rectangle, that's predictive of whether you're going to be getting a congruent spatial Stroop stimulus. Conversely, another color that gives you a certain probability, let's say 75% chance, you're going to be getting an incongruent spatial Stroop stimulus. And as a control, one that's both red and green and is basically non-predictive, 50-50. So these are different kinds of outcomes you could have. And what they found was that if you give people a cue that is incongruent with what they're going to get later, essentially you're inducing a prediction error, you get a reaction time penalty. So if you actually get an incongruent Stroop and the cue said it was probably going to be congruent, that's a big decrease in reaction time, or I should say a much slower reaction time. And conversely, if you're predicting an incongruent cue, but you actually get a congruent Stroop, you're also going to get slower reaction time. And they found that you found anterior cingulate cortex activity for comparing the trials where you would have a 75% congruent predicting cue and actually an incongruent Stroop stimulus. So we adapted this to two classes of stimuli. And notice that I'm giving an example right here where circles are representing shock and rectangles are representing a spatial stroop. In our actual experiment, they were counterbalanced both for color and also for shape, but for the sake of example, I'll run with this. So in this case, let's say I give you a circle, and you've been trained to know that a circle means you're going to be getting some kind of shock. You don't know if it's going to be painful or really just something barely noticeable and really not painful at all. Conversely, you may be getting a rectangle, and that tells you it's going to be a spatial stroop stimulus, but you don't know, based on the color, if it's going to be congruent or incongruent. So we have these two factors, 3 levels of each. In blue, in the case of shock, means 75% chance high shock, something aversive, something that somebody has subjectively rated as being aversive. And for the stroop, that means it's probably going to be an incongruent stroop. You flip the contingencies for the yellow, and also there's blue and yellow, which is basically uninformative. And then the actual outcome.
Is the shock painful or aversive but not painful?
We told them to calibrate it so that it's aversive but not painful. Yeah.
And the low level is just barely noticeable?
Low level is something that they notice but is not aversive at all. Yeah. So the first thing we looked at, based on this paradigm, notice that we're not only looking at, say, main effects of pain, main effects of congruency, for example. Those are pretty two simple things you can look at. But you can also look at prediction error. So if you thought you were going to get a high level of pain, but you didn't, or conversely, you thought you were going to get a low level of pain, but you actually got a high level of pain, we can look at those, combine them, and also see if that recruits a similar area of the dorsal anterior cingulate as, say, prediction error for the stroop tasks. So not shown is if you broke it apart into, say, prediction error for low pain, prediction error for high pain, same thing for the cognitive conditions, but there was a degree of overlap there. It wasn't significant because you lose a lot of power breaking it apart that much, but if you look at them when they're together, you do find significant overlap between the two types of prediction error. So I show this because we used that, we collapsed across then prediction error for pain, prediction error for cognition, and treated that as a single construct of prediction error. All right. So to actually answer these questions, is the dorsal anterior cingulate selective for pain? We approach this 3 different ways. The first one was an unbiased ROI analysis called a leave one out ROI analysis. So what happens here is, let's say in this case we had 26 subjects. You take one subject, remove them from the equation, you estimate your GLM with everybody who remains. From the resulting cluster within the medial prefrontal cortex, you extract the parameter estimate for that subject who was left out because they're not contributing to your GLM. You get one number for that, the average across that ROI, put them back into the GLM. You extract the next person, leave them out, estimate the GLM, repeat the whole sequence until you have one number per subject. And then you can do t-tests on that and test for interactions. So we found here if we have the magenta as the pain ROI, you do the leave one out subject analysis on that, pain is significant, but prediction error and conflict are not significant. And pain is significantly greater than either prediction error or conflict. You look at this in the more dorsal cognitive ROIs, the sequence flips. Now conflict and prediction error are significant, but pain is not. There's an interaction there. Another way we looked at this was through neurosynth to create ROIs. Now neurosynth is not only for meta-analyses, you can also use it to, well, first of all, carry out the meta-analysis, but then base an ROI on whatever search term you put in there. So we looked at the peaks activations for, say, prediction error, conflict, and pain. And we used those. We drew a 5mm sphere around the peaks of those activations, and we did the same ROI analysis. Now these 3 clusters, these 3 spheres are very close, but you can see they still seem to be spatially distinct. And again, pain was significant in the ROI defined by pain and neurosynth. And again, the whole pattern flips, reverses. Yes?
I just want to make sure I'm clear on the conditions that are going in.
Mm-hmm.
So is pain the stimulus intensity that you received irrespective of the cue that preceded
Yes.
it, or is that just the valid?
It's a main effect of pain collapse across predicted cues.
Okay.
So
and the
all high
prediction
shocks
effect
versus low
is
shocks.
both when you receive unexpected high pain, unexpected high intensity, unexpected low intensity, and the Stroop conditions.
Yes.
Okay. So no interactions here, right?
Oh, I'm sorry.
It's okay.
Okay. Maybe we can talk afterwards. But essentially, using another unbiased ROI analysis method, we found the same interaction holding. Okay. Last way we did approach this was through a data-driven method called k-means clustering. So in this case, what you would do is, in this case, we took a mask of the mPFC, and for each voxel, we gave it a matrix with 3 columns for each of the parameter estimates for that particular voxel. You do that across all the voxels in that ROI, do a k-means clustering, and you basically try to see if there's some kind of gravitational pull towards a couple of, say, the vectors, or maybe just one of them, or if there's some other pattern going on. You really don't know how it's defining it. But basically, it's trying to see whether, in some of these voxels, certain regressors cluster together. Certain numbers do. This is another way to create ROIs. And if we have the more ventral magenta ROI, we see that our pain is again significant there, not significant for conflict or prediction error, and this pattern again flips in the more dorsal green ROI. So 3 different ways we address this question.
Did you try that with 3 clusters?
We did. We got a pretty similar result, but the thing is, it's when we did a silhouette method to estimate the optimal number of clusters, it said 2, which makes sense. We only had 3 regressors going into it. Yeah. So revisiting our questions. Is pain within the dorsal anterior cingulate cortex? I would say yes, and that's not controversial at all. Whether it's selective, we can't really say right now. Right? But as far as pain being within the DACC, that appears to be yes. Now, are cognitive effects within the pre-supplementary motor area? Let's go back a bit and focus on something called the cingulate sulcus, a very prominent anatomical landmark. It is defined as the dorsal boundary of the dorsal anterior cingulate cortex if you're looking within the mPFC. So if I trace this out right here, that is about your cingulate sulcus, at least on this template MNI brain. Now it looks here as it looks here as though pain actually does fall ventral to that, and the cognitive effects are a little bit more dorsal to it. So if we were just using this template brain, so much what Lieberman and Eisenberger did, we would conclude that, yeah, actually these 2 things are distinct, and pain seems to fall within the dorsal cingulate, and the other effects are in the pre-SMA. However, this is getting back to what I was talking about with individual anatomical variability. This again is another figure from that Shackman paper looking at an additional structure called the paracingulate sulcus. I wasn't aware of that until I read this paper. And apparently within about 60-70% of the population, people have an additional sulcus called this paracingulate sulcus. And it's not trivial. It's not small. It's not inconspicuous. It's actually quite large. It runs dorsal to and roughly parallel with the cingulate sulcus. When you have this double folding of the cingulate gyrus. And now we have not only the cingulate gyrus, but another thing highlighted in green here called the paracingulate gyrus. So now in this case, if everything north of the cingulate sulcus is pre-SMA, if you have a paracingulate sulcus, now everything dorsal to that is pre-SMA. Does that make sense? Okay. Now why this might be a big deal is if you're looking at a second level analysis and say both of these subjects have been warped, normalized to the same stereotaxic space. If I look at an, okay, too much to handle. 1 second. Okay. So the reason this is important is if I look at the same coordinate, the same XYZ coordinate across both subjects, and I have a voxel right here, or say a peak activation right here, this falls ventral of the paracingulate sulcus, and so we would classify that as being within the dorsal anterior cingulate cortex. Whereas in somebody who does not have a paracingulate sulcus, which tends to take up more real estate in the medial prefrontal cortex, you would say that this would actually be within the pre-SMA. I'm going to refer to a few studies by Celine Amias, who's done a lot of work on this individual anatomical variability because, again, it's not trivial. It's a very large structure, and she found that it makes a big difference on where you localize your activation. So in somebody, and this is the same subject, mind you, you can have a paracingulate sulcus in the left hemisphere, a paracingulate sulcus just in your right hemisphere, or a paracingulate sulcus in both. Come in all flavors. What she found is that you can have the same subject, you look at the hemisphere without a paracingulate sulcus. And the peak activation lies within the cingulate sulcus. And if you look at a same subject, opposite hemisphere, which happens to have a paracingulate sulcus, the peak activation lies within the paracingulate sulcus, but is not significantly active within the cingulate sulcus. This can be a difference of 5, 6, 10 millimeters sometimes in the most extreme cases. If you look at a group level, it makes sense why it might make sense to take this into account. On the top left there, if we take an average across all the anatomicals of people who do not have a paracingulate sulcus, I've traced out the cingulate sulcus in red. And their activation, it's both a little bit dorsal to that, but it also bleeds into the cingulate sulcus and within the dorsal anterior cingulate.
What is this activation affecting?
It's feedback-related activity, so it was a prediction error experiment. If you look at only the paracingulate sulcus group, again, you do not find significant activity in the cingulate sulcus, highlighted in red, but it falls along the banks of the paracingulate sulcus, highlighted in green. If we were to take the average of those two, you would find that it would seem as though this feedback-related activity is within the pre-SMA and not the dorsal anterior cingulate cortex, when in fact, there's a lot of evidence to suggest that it tends to bridge both of those regions. If you went back to the diagram by Lieberman and Eisenberger, that would seem to suggest that, yes, their activity, or say prediction error conflict, is actually within the pre-SMA. But if you were to look at a single subject level, or at least a subgroup level, you would find that it tends to be across both. What we did then to address this was we classified subjects as either having a cingulate sulcus or a paracingulate sulcus. So on the top here, again traced out in red, is the cingulate sulcus. This is just an example subject. Now on the bottom is a hemisphere that has a paracingulate sulcus and a cingulate sulcus. And by the way, everybody has a cingulate sulcus. It's only a certain percentage of people who present with an additional paracingulate sulcus. So when we did that, we looked at the averages across the cingulate sulcus only group and the paracingulate sulcus group. And we're looking here at prediction error because that was our strongest cognitive effect. And basically, since we were dividing people into these subgroups, we were losing some power, so we tended to just focus on that. The conflict effects were not significant if we just divided it into groups. These are thresholded to show the extent of activation at p less than 0.05 uncorrected, but also cluster corrected at 0.05, so not necessarily Eklund approved, but I want to just point out the actual spread of activation for these different feedback-related activities. In the cingulate sulcus group, again, you find this prediction error activity, again, tends to bridge both the pre-SMA and the dorsal anterior cingulate. And if you look within the paracingulate sulcus group, corroborating the research done by Celine Amias, you find that activation primarily within the PCGS, but not within the cingulate sulcus. Going back to our template brain here, if we take the overlap between them, if I was just to show this to you, just this part in yellow here, the overlap between the two groups from our second level analysis. This is all pretty distinctly above this cingulate sulcus right here. And it's obvious why you would tend to classify that as a pre-SMA. But you can see if we broke them apart, it tends to bridge both across both the cingulate sulcus group and the paracingulate sulcus group. So what can we conclude from this? One, again, is that pain, not surprisingly, is located within dorsal anterior cingulate cortex, replicating virtually every study that's done pain ever. Not surprising. But cognitive effects span both the dorsal anterior cingulate and the pre-SMA, suggesting that the DACC is not selected for pain, but rather seems to subserve both to some degree, even though pain seems to be more significant the more ventral you go. So maybe it's a gradient, we're not exactly sure. And lastly, this is actually the title slide of my talk, but I moved it because I didn't want to give the show away. So there's some suspense, so you're thinking about what might happen. Distinct regions within medial prefrontal cortex process pain and cognition. Okay. Thank you again for your time. I'd like to open it up to questions at this point.
Quick question about the paracingulate sulcus. So, did you say 60 to 70% of people have it?
Yes, yeah.
So, and there's a difference between the left and the right. Is there a bias towards?
Not that I've seen, at least in our sample, it was nearly equal, the amount that just had it in, say, the left and the ones who just had it in the right. And I didn't test for this, but I may not have the power. I'm not sure whether you would find a systematic difference between the two groups. I can't say, but I don't think that you would. Yeah, Adam.
Why not do a surface analysis if you have these differences in the anatomy? Wouldn't that be the quickest way to sort these things out?
Yeah, I agree. That would be the reasonable next step to do, for sure. Yeah, I will do that. Yes, that's all I can say.
Thank you. It's really interesting. Thank you. I have a question. So you make a distinction, I think a pretty strong distinction between pain and cognition.
Mm-hmm.
And one could argue that there might be not such a strong boundary between the two things, right?
Right.
Pain always has a cognitive component.
True.
Prediction error, working memory, there's always some sort of affective signal going on as well. Like you get a cue and it turns out to be wrong. Like damn it, got it
Mhm.
wrong again. So there's also an affective
True.
component to so
Yeah.
how would you address that?
Yeah, again, the maps that I did not show, mainly because of the trial yield, was breaking apart the prediction error for unexpectedly high pain and unexpectedly low pain. Now, they were roughly in the same area. We couldn't say anything conclusive because they didn't pass the significance threshold. But my guess is that since we found a pretty strong main effect collapsing across both of those, and also the overlap within with the cognitive prediction error, I would say that they're roughly the same, I would say. We also have a computational model that we worked on back at IU about the medial prefrontal cortex, hypothesizing that it's not necessarily the valence of the feedback that you get or the prediction error that you get, either unexpectedly good or unexpectedly bad. They seem to recruit the same patch of cortex in the dorsal anterior cingulate. So in other words, if you won the lottery, that's a really good thing, but you're not expecting it, right? We showed that you would find roughly the same amount of activity and the same localization of activity for that unexpectedly good result as an unexpectedly bad result. That was in a monetary condition, and again, we didn't have the power for this, but I'm pretty sure that you would, if you had enough trials, enough subjects, you would find the same.
Take your word for that.
Oh, but yeah, just trust me. What we all want. Anything else? So if there are no other questions, I might as well talk about some other ideas I've been having. Everybody here knows who Herman Melville is? Yeah, I promise there's a point to this. So he wrote Moby Dick, right? Which is undoubtedly a supreme contribution to world literature. It's also a really weird book. And when he published it, he was coming off a string of very successful novels. As he's writing Moby Dick, he thinks this is actually going to be terribly received. I think it's probably the best piece of art I've ever made, but people are going to hate it. And they did. And he spent 4 decades of his life until the day he died, miserable and unsuccessful and forgotten. It's terrible. It's a lot of anguish. But he made the choice to do it anyway. When we're talking about pain, there's been a lot of research with things like empathic pain, right? Seeing somebody else suffer, getting more into things like social aspects of pain. And when I heard that story, it made me think, why did he do that? What makes somebody willing to endure intense social ostracism or even pain on behalf of their artistic integrity or for some kind of belief? Right? It's extremely rare, at least in this country nowadays, people be tortured for a political or religious belief, but social exclusion, ostracism, is not so rare. And I'm guessing everybody here has felt that at one point or another for an opinion they've held or a belief they've held. If you've never felt that, you should write a book, because people want to know how you do that. Maybe it's just being really boring. But the point is, actually enduring pain for the sake of some goal, maybe to spare somebody else for feeling pain, maybe enduring some kind of pain or even social rejection based on some cause that you believe in. As far as I know, this hasn't been intensively studied from an fMRI point of view, but it's something I'd be very much interested to look into. Thank you again for your time.
I mean,
Yeah.
there
Oh, sorry.
is a big
I'm sorry
body
about
of
that.
literature
I jumped the gun. Yeah.
on moral decision making and how much you'll take pain for other people and stuff like that. There is kind of in the social neuroscience field, actually, I think a lot of work, not necessarily
If you're
going into the pain,
Right.
social pain versus physical pain
Mhm.
kind of modality, but there's
I'm curious, so have they done that if you're, say, linked up to another person in another scanner? Really?
Yeah.
Okay.
Yeah.
I was looking for that, and I wasn't able
I
to
think,
find it.
yeah.
Okay.
We can talk about that.
Sure.
Sorry.
That's okay. Anything else?
Thanks.
Thank you.